Hello, my name is Arnaud Delorme, and this is part 2 of a series of videos on time frequency analysis of EEG time series. This part is about the EEG spectrum and EEG event-related spectral perturbation, or ERSPs. In some cases, when a signal here is sinusoid at 100 Hz is sampled at a given frequency, here at 80 Hz, the resulting samples, so the dots here, might be indistinguishable from those of another sinusoid at a lower frequency. This is called aliasing frequencies, and these aliasing frequencies can be calculated using this formula in red, where we vary an integer n. In this case, using this formula, if we set n to 1, we obtain the aliasing frequency of 100 minus 80 equals 20 Hz. How can we be sure to recover the original sinusoid signal? That's the concept of Nyquist frequency. The Nyquist frequency is the maximum frequency that can be uniquely recovered at a given sampling frequency, and it is half the sampling frequency. So in this case, since the sampling frequency is 80 Hz, we cannot recover at a signal that at a higher frequency than 40 Hz. If you are interested in processes in the gamma range of EEG, so 40 to 80 Hz, you need to collect the data with a sampling rate of at least 160 Hz. So let's look at a related concept, which is ZeroPadding. The Fourier transform of a sequence of length n produce power estimates at n frequencies evenly distributed between 0 and the sampling rate, or n divided by 2 frequencies between 0 and the Nyquist rate, since we usually do not look at frequencies above the Nyquist rate. Padding the signal with zeros on both sides achieves two things. First, it allows enforcements of a signal of length as a power of 2. That helps with the mathematical trick implemented in the Fourier transform, which I mentioned in a previous video. Second, it artificially increases the number of frequency bins. So if you have 200 samples in 1 second, you would get 200 frequencies from 0 to 200 Hz. Now if you're padding with 100 zeros on each side, now you have 400 samples, so 400 frequencies from 0 to 200 Hz. So you have effectively doubled the number of frequencies. This is shown here in this plot with the blue dots representing the non-zero padded version and the red line representing a heavily zero padded version. Not that this should not be considered as this should only be considered as a type of interpolation or smoothing method, as it does not increase frequency resolutions. In other words, it's not the same as doubling the sampling rate because you do not add any new information. With Fourier transform, we may exactly represent any continuous stationary signal of length n using a weighted sum of n sinusoid. So if you have a discontinuity in your signal, how can you represent that using a limited number of smooth sinusoids? Well, you can't. Here in red, we have a step signal, which is approximated using 2, 4, or 8 sinusoids. We observe ripples in a reconstructed signal due to the discontinuity, and these are due to a phenomenon called the Gibbs phenomenon. And the same phenomenon happens at the edge of EEG signal, or if we have an EEG signal padded with 0 as shown here. And here we have another discontinuity, a Dirac signal that is also approximated using 2, 4, or 8 sinusoids and shows ripple in the reconstructed signal. So if we wanted to get rid of these ripples, we could use an infinite number of sinusoids at different frequencies, which means we would need a signal with an infinite number of samples, since the number of frequencies depend on the number of samples. And of course, it's not possible. So what can we do? We can taper the data, which means multiplying the signal with a smooth signal that decays to 0 at the edges. Here we multiply the EEG signal with a red Gaussian signal, also called a taper, and we obtain an EEG signal with no sharp edges. So tapering reduces the effect of Gibbs phenomenon. Here we can see that the amplitude of the ripples is much lower for the tapered signal compared to the untapered signal. However, the cost is an increased width of the central peak, which also means loss of resolution. The reason that the central peak increases in width when side ripples are suppressed is because the total variance may remain constant. In suppressing Gibbs ripples, we are simply shifting energy out of frequency distributed over the entire spectrum into frequencies near the central peak. Now let's look at how to compute the spectrum of an EEG signal. A method which is usually widely used is called the Welsh methods. It consists in segmenting or slicing the data into different windows and tapering them as I've shown before. For each window at a given frequency, we obtain a phase vector, and then we can average the length, the square length of this phase vector to obtain the spectral power at that frequency. If there are k segments, this reduces the total variance by a factor of k. It also reduces the frequency resolution by a factor of k. But the loss of frequency resolution is usually not so important from the user standpoint. If you have 1 second segment, it means that your frequency resolution will be 1 Hertz, which is acceptable in most cases. Here, a potential problem is that tapering may result in data loss. We are missing the data at the edge of the taper since it has been zeroed out. So how can we mitigate this data loss? We can simply have the window overlap as shown here. Then we average the square length of the phase vector to obtain spectral power as we did before. And now we can have the best of both worlds, spectral variance reduction and reduced data loss. You can also have data trials in EEG. So in addition to segmenting the data and averaging spectral estimates over the segments, you can also average spectral estimates across trials. And if you have n independent trials, this will further reduce the variance by a factor of n. Up till now, we have assumed the signal as stationary, which means that the statistics of the signal doesn't change with time. But most EEG signals don't have this property. For example, here we have an alpha burst, as it might occur in the lateral visual system following the presentation of a stimulus. Our examples of non-stationary signals include evoked potential and chirp. We can extend the concept of spectral decomposition of stationary signal to spectral decomposition of a time window, where we use a sliding window across a signal and obtain a spectral estimate across at each time. This allows us to produce a spectrogram, which is also called time-frequency image. If we have multiple trials available, we can average to improve our resolution and further reduce variance. Because the spectral change are following the presentation of a stimulus or event, we call these event-related spectral perturbation. This is the equation which is being used to calculate event-related spectral perturbation. You can see that at a given time in frequency, you can simply average the square of the length of the phase vector across trials. Usually, when looking at this measure, we scale them to dB by simply taking 10 times the base 10 logarithm. This way, it's easier to visualize change in spectral power. Something else we usually do with this spectral image is to remove the baseline so it's easier to visualize spectral changes following the presentation of a stimulus. Here's at time 0. So at each frequency, we calculate spectral power before the presentation of the stimulus, and we subtract this average value from the values at all time windows. And we do that for each frequency separately. So this is the resulting image. And you can see that it is much easier to visualize spectral changes following the presentation of a stimulus. Here we can see an increase at 10 Hertz and another decrease at 30 Hertz. And I want to mention that there are different ways to compute this baseline. I've included a reference here where we discuss this subject. So I want to thank you for your attention, and I'll see you in the next video.